Welcome to our session on F distribution moments. Today we are going to explore the mathematical center and spread of one of the most important probability curves in statistics. Whether you are comparing manufacturing machines or analyzing medical trials, understanding these moments is absolutely essential. Let us dive in and build this from the ground up. Now that we know what we are studying, let us understand what moments actually are. Imagine balancing a heavy tray of drinks. The center of mass tells you where to place your hand, while the spread tells you how wobbly it might be. In statistics, moments do the exact same thing for data. The first moment gives us the mean, or the balancing point. The second central moment gives us the variance, which measures how spread out the data is. The F distribution is a right-skewed curve, built by taking the ratio of two chi-square distributions. Because it is a ratio, it has two sets of degrees of freedom, m for the numerator and n for the denominator. Building on those degrees of freedom, let us look at the mathematical formula for the mean. Conceptually, this formula tells us where the F distribution balances. Surprisingly, the numerator degrees of freedom m does not even appear here. The average value is controlled entirely by the bottom part of the ratio, n. In this equation, E of f represents the expected value, and n is the denominator degrees of freedom. There is a strict condition. N must be strictly greater than 2. If n is 1 or 2, the math does not settle on a finite number, making the mean undefined. As n gets very large, the fraction approaches 1, meaning with massive amounts of data, the average f value settles around 1. Now that we have our balancing point, we need to understand how to calculate the variance, which tells us how widely the data scatters around that mean. This formula is more complex because it incorporates both sets of degrees of freedom. Conceptually, it measures the wobble of our data tree. Here, var of f represents the variance. The variable m is the numerator degrees of freedom and n is the denominator degrees of freedom. Notice the strict condition here. N must be strictly greater than 4. If n is 4 or less, the denominator becomes 0 or negative, making the variance infinitely large or undefined. Physically, as both m and n increase, the overall variance shrinks, meaning more data points make our distribution much narrower and more precise. Before we move on, let us see this with a concrete example. Suppose we are comparing the variances of two manufacturing machines to see which is more consistent. We are given an F statistic with numerator degrees of freedom m equals 5 and denominator degrees of freedom n equals 10. We want to find the exact mean to establish a baseline. First, we check our condition. Is n greater than 2? Yes, 10 is greater than 2. We choose the mean formula because it gives us the expected balancing point. We substitute 10 for n in both the numerator and denominator. Subtracting 2 from 10 gives us 8, and 10 divided by 8 results in 1.25. Physically, if we repeated this comparison thousands of times, the average F statistic would settle exactly at 1.25. Continuing with the same manufacturing machines, we now move on to finding the variance. We know m equals 5 and n equals 10. First, we must verify our strict condition. Is n greater than 4? Yes, 10 is greater than 4, so the variance is well defined. We write down our full variance formula to measure the spread of our data. We carefully plug our specific values of 5 and 10 into every corresponding spot in the fraction. It is crucial to place the numbers in the exact right positions to avoid calculation errors. The numerator gets the 10 squared and the sum of the degrees of freedom. The denominator gets the 5, the 10 minus 2 squared, and the 10 minus 4. Let us finish calculating the spread for our machines. We begin simplifying the expression by following the standard order of operations. We resolve the addition and subtraction inside the parentheses first and square the 10 in the numerator to get 100. This breaks the large, intimidating formula down into manageable pieces. Multiplying the terms in the numerator gives us 2600. In the denominator, squaring 8 gives 64 and multiplying everything together yields 1920. Finally, we divide the numerator by the denominator. Our final variance is approximately 1.354. Physically, this value represents exactly how widely our F statistic will scatter around our mean of 1.25 during repeated sampling.
Now that we have calculated these moments, let us visualize what they actually look like. Here you are seeing a graph of the F distribution. The horizontal axis represents the F value and the vertical axis shows the probability density. Notice the three different curves. The wide, flat blue curve represents low degrees of freedom, specifically 5 for both numerator and denominator. As we increase the degrees of freedom to 10, shown by the red dashed curve, and then to 50, shown by the black dotted curve, two physical changes happen. First, the peak of the curve shifts, and the balancing point, or mean, approaches exactly 1.0, marked by the vertical dashed line. Second, the curve gets much taller and skinnier, which perfectly illustrates our variance decreasing. More data means less wobble.
This visual understanding leads us to a fascinating and highly useful trick built into the F distribution, called the reciprocal property. Why does this matter? Sometimes in research, you need to analyze the inverse of your data ratio. Calculating the moments of an inverted variable directly using calculus is incredibly difficult and time-consuming. The reciprocal property gives us a shortcut. It states that if you flip an F-distributed fraction upside down, it creates a brand new F-distribution. But here is the magic part. The degrees of freedom also flip. The old numerator becomes the new denominator and vice versa. Historically, this was incredibly helpful because old statistical tables only printed values for the right tail to save paper. You could just flip your numbers and look up the reverse distribution instead.
Let us look at the exact mathematical notation for this property. Conceptually, this formula shows the transformation of our variable. The symbol that looks like a tilde means follows the distribution of. So, if our original variable f follows an f distribution with parameters m and n, then the inverted variable 1 over f perfectly follows an f distribution with parameters n and m. The m is the original numerator degrees of freedom and n is the original denominator degrees of freedom. When you invert the variable, you simply swap their places. This simple swap allows us to calculate lower tail probabilities and makes calculating the moments of inverted ratios incredibly easy. You just treat the inverted variable as a normal f distribution with swapped parameters. Let us see how this property saves us time with a real example. Suppose you are analyzing data from a biological study. You have an F distribution with numerator degrees of freedom m equals 8 and denominator degrees of freedom n equals 6. However, your software requires the mean of the reciprocal of this distribution, 1 over f. Instead of doing complex calculus, we use our property. We define a new random variable y to represent the reciprocal. Because of the property, we know y follows a new f distribution where the degrees of freedom are perfectly swapped. The old n of 6 becomes the new numerator and the old m of 8 becomes the new denominator. This setup turns an impossible math problem into a simple arithmetic one. Continuing with our biological study, we now calculate the mean for our new variable y. Remember, the expected value formula only cares about the denominator degrees of freedom of the distribution it is applied to. We call this new denominator n nu to avoid confusion. We quickly check that n nu is greater than 2, and since 8 is greater than 2, we can proceed. We write down the standard mean formula and substitute 8 into both the numerator and the denominator. We subtract 2 from 8 to get 6, leaving us with 8 divided by 6. Our final answer is approximately 1.333.
Physically, this means the balancing point of our inverted data is exactly here, found effortlessly by just swapping two numbers.
So, we have proven that these calculations work. This brings us to an important question. Why does all of this matter in the real world? The F distribution is the absolute backbone of a technique called ANOVA, or analysis of variance. This is used everywhere, from medical trials to agricultural testing, to compare multiple groups at once. For example, when a pharmaceutical company wants to know if three different headache pills have different effects, they use an F test. The moments we just learned to calculate tell the statisticians exactly what a normal result looks like if all the pills are actually identical. If the test result falls way outside the expected spread defined by our variance formula, the company knows they have found a genuinely better pill, not just a random fluke. Let us wrap up and reinforce the most important ideas we have covered today. First, the mean of the F distribution gives us the mathematical center, and it depends entirely on the denominator degrees of freedom, requiring n to be greater than 2. Second, the variance gives us the spread, depending on both sets of degrees of freedom and requires n to be greater than 4. We also saw how increasing data points makes the distribution narrower. Finally, the reciprocal property allows us to flip the distribution and swap the degrees of freedom, making complex calculations incredibly simple. You have now mastered the foundational properties of the F distribution, which is your first major step toward comparing multiple groups of data in the real world. Great job!